Our next presenter is Dr. Divya, and if I can invite her. The topic is mobile autoperimetry.
This is incredible. Virtual reality is about to take off in a way that I don't think anybody can fully comprehend.
We are in the very early innings of what is AR and VR and what we describe as mixed reality.
We're here to make virtual reality the next major computing platform.
I think that virtual reality is the most important technology in the history of humanity.
New mobile autoperimeter using virtual reality, perimetry, a test procedure that is used to diagnose many ocular and neurological diseases, is the systematic measurement of the visual field, a portion of space visible when gazing in one fixed direction. It is measured in terms of differential light sensitivity units and primarily revolves around detection of a small target on a uniform background. In 1856, Albrecht von Graefe quantitatively measured the visual field for the first time. In 1889, Yannick Bierum used a tangent screen to demonstrate early field losses in glaucoma. In 1945, Hans Goldmann developed a hemispherical ball perimeter with a movable projector that standardized perimetry measurements. By early 1970s, computer-controlled automated perimetry was developed. Instruments made by the Octopus and later the Humphrey companies have become nearly universal. Standard automated perimeters have been the preferred option for visual field testing for the past 30 years. However, these devices are bulky, need a specialized darkroom, restrict patient posture that rules out patients with special needs. Also, the high cost of computerized field analyzers drives the cost of field examinations, thereby limiting the reach of visual field examinations in the developing countries, resulting in vast prevalence of undiagnosed glaucoma. In order to overcome these challenges, a mobile autoperimeter is proposed. The mobile autoperimeter consists of a head-mounted device, a patient response button, and a test control unit. The head-mounted device has a visual display unit with an inbuilt microprocessor, infrared cameras to track the pupillary movement, and lenses that direct the image on the tested eye. Test is conducted by presenting stimuli using stereoscopic projection. Patient response during a visual field test is captured using the patient response button that is paired with a head-mounted device via Bluetooth. The test control unit can be a PC, a laptop, a tablet, or even a mobile. The test control unit is paired to the head-mounted device wirelessly through a cloud-based data connection. The examiner can log in on the control unit and set up the test for a patient. Test report displays the results. It consists of date and time of test, patient information, test time, absolute threshold values, a gradient plot based on the threshold results, a readout of reliability parameters such as false positives, false negatives, and fixation losses. An AMOLED screen with Quad HD resolution is used. The display is magnified by an aspheric lens to cover a field of 80 degrees at each eye. Binocular optics separate the images presented to each eye, and there is no need for occlusion while conducting tests. Standard field analyzers use a spherical background where all stimuli are at the same distance from the tested eye. However, in the mobile autoperimeter, the distance from the eye is a function of eccentricity. In order to conduct the test at locations comparable to those on the Humphrey field analyzer, locations of stimuli are determined considering spherical projection transformations, field curvature, and distortion at the lenses. Threshold measurement is done by measuring the differential light sensitivity keeping the background maintained at 9.6 candela per meter square, and a measurement scale of 0 to 40 decibels is achieved by changing the intensity or the size of the stimulus. Using the logarithmic scale developed for the mobile perimeter, it is expected that the results are 2 decibels higher when compared to those of the Humphrey field analyzer. In order to keep the test algorithm short without losing accuracy, a modified ZEST algorithm with 20 decibels initial guess values were used. In addition to this, the test strategy has false positive, false negative, and fixation loss catch trials. The mobile autoperimeter was programmed to conduct a 24-2 field test using white-on-white perimetry. The aim of the trials was to establish the device test-retest variability and comparison of the global indices with that of Humphrey. 12 normal patients were tested 3 times each. Variation of mean sensitivity and standard deviation with eccentricity is as expected for normal patients. This performance is in line with other existing visual field analyzers. It was observed that mean deviation of 1.8 decibels as against an expected deviation of 2 decibels. The spread of differences was observed to have a standard deviation of 2.5 decibels and is in line with other field analyzers. In addition to this, it was found that the test time on the mobile autoperimeter was approximately 3 minutes longer than the CETA standard test on the Humphrey field analyzer. Initial results show that a portable autoperimeter can be used to conduct perimetric examinations. We plan to improve our test strategy to further reduce test times and conduct field trials to build a population normal database. The mobile autoperimeter offers a chance to break free of the traditional constraints of in-clinic testing. The device can be programmed to perform other vision function examinations such as color vision testing, diplopia charting, contrast sensitivity, depth sensitivity, ocular motility, and visual acuity, making a one unified device for comprehensive visual function evaluation. It is time to embrace the next big thing in ophthalmology. Virtual reality is here to stay. Try it to believe it.